Hello, welcome back to Fixed Income course. Today we are going to look at a fixed coupon bond. What is a fixed coupon bond? It is the bond that, apart from the notional at the end, at the maturity, will pay fixed coupon annually or semi-annually until maturity. In this video we are going to create a Python class called bond, in which we will define two methods: how to price a bond and how to calculate yield to maturity of a fixed coupon bond. In order to calculate a yield to maturity, we will use so-called Newton-Rhapson method. Okay, let's get started. So let us define a class in Python called bond. And in this class we're going to define a constructor first of all, def init. It will, apart from self keyword, it will take two attributes. First of all, maturity, and secondly, the coupon. In the constructor we will assign these variables to class attributes. So self maturity will be equal to maturity, and self coupon will be equal to coupon. Let's agree that the coupon will be paid annually for simplicity, and it will be expressed in percentage points. Okay. So we have the constructor. Now the first method that we're going to define is going to be present value. How to calculate the present value of this bond. So we need to reuse self keyword, and for calculating the price we'll also need the interest rate that is currently in the market. So let's call it R. Let us look at the formula, how the PV of a bond is calculated. So what PV is a sum of discounted cash flows that the bond generates. So first of all, this is a notional, which is discounted back from maturity. We use n as a maturity, so we divide by 1 plus r to the power of n. And then for each year, from year 1 till maturity, we have to also take coupon into account, and we discount it by the discount factor that is corresponding to each year. Okay, so this is the formula. Let us implement it in Python. We have it here. Let's define sum variable in which we will sum up all the cash flows. And let us first use the notional cash flow. So this is 100. And here we need the power, because we need to have a discount factor to the power of n. So let us import a Python library called math. Import math as m, and this library will have a power method. So we're going to use it here. We're going to use m pow for power. The base will be 1 plus interest rate, and the power will be maturity. So in our case this will be self maturity. And because we are dividing, we need to take a negative power. Okay, so we have the sum initialized. Now we need to add up all the coupons. So for that we're going to use a for loop. We're going to loop for each year. So for I in range. So we need to start a range from year 1. Python function range by default starts from 0, so we need to specify explicitly 1, and it will loop until self maturity, and here we also need to add 1 so that the last iteration will be with I equal to self-maturity. And for each of those iterations, we're gonna increment the sum by the coupon. So basically we need to write self coupon, and we also need to discount it. So we can copy this thing, but right now the power will be not the maturity but each corresponding year. So in our case this would be simply I. And we're gonna return obviously sum. Let us for clarity round it up to 2 decimal places. Okay, so we have this method. Let us test it now. So let's define an instance of this class. Bond is equal to bond. Let us choose maturity first. So let's say we have 10 years, and coupon, let's say 4%. So first of all, what we want to see is we want to print what will be the PV for this bond. So let's call this method bond PV, and let's say for sanity check, let us see what will be the PV of this bond if the interest rate is exactly the same as coupon. Why is this interesting case? Because if interest rate on the market is 4% and the coupon pays 4%, that means that it is at par, at fair value, let's say. So the coupon exactly compensates for the interest rate on the market, and the price should be equal to 100 in this case. Let's check if we got it right. Yeah, we printed the price as 100 exactly as we expected. Okay, let us use this PV of the bond function to see what is the relationship between the interest rates and PV of the bond. So let us first define an array of interest rates. Let's call it IR. Let's generate interest rates from 0 to let's say 10. So we're going to use a for loop here as well for I in range. So if we start from 0, we can just write one argument, and this will loop from 0 to 9. So actually, let's write it like this. So first define the range here. And now loop through it, and for each of those, let's generate the PV of the bond. So this one we will call PVs, and we're gonna call this bond PV. We're gonna use this interest rate I, but I is just from number from 0 to 9, so we need to multiply it by 0.01 in order to get percentage. Okay, so we have this range of interest rates and corresponding present values. Let us also plot it. Let's import another Python library called matplotlib. We used it in the previous episodes as well. Pyplot as PLT. So first of all, PLT plot. So we create this plot, and we're going to plot interest rate against PVs. Okay. Let us also add the grid to our graph. So we just write through here, and let us show that graph. PLT show. Let's run it. Okay, so we have a graph. So couple of things to notice. First of all, the higher the interest rate, the lower the price of the bond. So as Financial Times famously puts it, bond prices and interest rates are inversely related. Second, as we saw before, the percent interest rate at which the PV of the bond is equal to 100 is 4%. So exactly the same as coupon. And third, notice that this is not a straight line, this is a convex line. This in bond theory is called bond convexity. Why is it convex? If we look again at the formula of present value, we see that the dependent variable r is a factor by which we divide. Okay, so this function, PV function, is hyperbolic in nature, so that's why the graph here is also slightly hyperbolic. It's not too much because this factor is close to 1, but it is a bit convex. If you, like me, had a problem of telling apart which function is convex and which function is concave, because for me, if you look from the other side, it's just one function that is convex from one perspective is concave from the other side. So you just need to remember that the bonds are convex, and if you remember this graph, you will remember which function is convex and which is concave. Okay, so we have a present value now. Let's now move over to yield to maturity. What is a yield to maturity? It is a interest rate for which the present value of the bond is equal to its price. Okay, so this is the yield that the bond is generating based on the current market price, in other words. So how can we get this? Let us rearrange this equation a little bit so that we see a function here which is equal to 0, and we're going to look for a root or a 0 of this function. So if we expand this term here, our function becomes, this is the PV bit that is dependent on interest rate minus price is equal to 0. So if we solve for r, this solution that we'll have is going to be equal to yield to maturity. So let's first try to look at this equation a little bit. So what it would mean to solve for r? Well, probably the first thing that we would like to do is to multiply by 1 plus r to the power of n, so that we get rid of all the hyperbolic terms, and instead we have a polynomial which will also be of order n. So polynomial of order n is not exactly the easiest thing to find analytical roots of. So what we're going to do instead here is we're going to use so-called Newton-Rhapson method. This is a numerical method that we use for root finding of a nonlinear functions. How does it work? It is based on the idea of approximating a root of a nonlinear function by possible roots of a linear function that is basically tangent to that nonlinear function. What does it mean exactly? Let's take a look at the math. So here we have a definition of derivative. This is just a high school definition, nothing fancy. So this is the limit of this ratio. Change in function divided by the change in argument as one argument approaches the other. This is true for all functions that have the derivative. If the function is linear, we can say a little bit more, because this ratio is constant. Derivative of a linear function is constant, this limit is constant, and also this ratio is not dependent on the choice of those 2 points. It will always be the same. So if we want to use this fact about a linear function in order to find value at x1, we rearrange this equation a little bit that we have here, and the value at x1 is the derivative, so this is the increment that we have for this function. Here we have a difference in the arguments, and of course we have the starting point from which we increment. Yeah. And the next step is that if we want to find the root of a linear function, then we basically say that, okay, so this ratio is 0. This equation is this term, this this value of this function x1 is equal to 0, and then we solve for x1, so that we see at which point the linear function crosses 0. If we solve this equation for x1, we end up with this relationship. Okay, so based on a definition of a derivative, we can calculate a root of a linear function in this way. This is always true for a linear function. The idea of a Newton-Rhapson method is to use this approximation and see how does it work for a nonlinear function. Okay, so let's try it out. First of all, we need to calculate the derivative of our function. Okay, so we have our function f of r defined here. So let us now calculate the derivative of it. So here we rearrange the terms a little bit so that we see that here we have a negative power and here as well, and this is so that we can more easily calculate the derivative of such function. So we remember that if we have a function of this form, in order to calculate the derivative, what we need to do is we need to multiply each term by the power. So in our case this will be minus n for each of those terms, and we need to decrease the power by 1. So here we have minus n minus 1. And this is also the case here, but we multiply by minus I, and here we have minus I minus 1. Okay, so let's now implement this derivative function into our bond class. Let's copy the PV function, PV method that we have here. Let's call it now PV derivative. So what we need to do here is we need to multiply by minus maturity. And here we also need to decrease the power by 1. And the same thing here. Minus I times this term minus 1. Okay, so this is the derivative of our present value function. Notice that this derivative will be the same for the present value function as well as present value minus price, because the price is not dependent on interest rate, so it is a constant. So if we take a derivative, this term will disappear. Okay, so now let's see graphically how this Newton-Rhapson method would work. So what we want to do is we want to generate, we want to take a point on the graph. Let's say that we start from 0. Okay, we as our initial, let's say, starting point, our guess for the root. From that point, we look what is a tangent line to our function. So let's write a function called tangent. It will be actually, well, an array as well. Maybe first of all, let's change this function here. Let us define a price, which let's say is going to be 91. And for each, we're gonna decrease it by this price, so that we have this full function PV minus price. Okay. Let's quickly see what the graph will look like, so that we see that we are indeed looking for a 0, for a root of this function. Yes. So here, when we decrease by price, we see that the root, or the yield to maturity, will be somewhere between 5 and 6%. Okay. Now let us look at this tangent function. So we also going to have to generate some values for each of those interest rates, right? Like we did in here. So what is it going to be? So first of all, we need to have at point 0. Let's start at the point 0. So at the tangent line at the point 0 will be simply the value of this tangent function will be the same as the original function. So we're gonna use bond PV at 0, right? Now and minus price, of course. We also need to adjust for the price. Then for each of this interest rate, we will increment by the same amount, because it's going to be a linear function. So what is going to be this amount? Well, this will be exactly the derivative of our function. So this will be the function that we already have, the method that we just defined, called bond PV derivative, also at point 0. And also we need to multiply by 0.01 here, because I is just a integer and we want to have a absolute number. Okay, let's try to run this one and see if we got it right. And we also, of course, we need to add it to the plot. So we're going to copy this, and we're going to add a tangent line. Yeah, exactly. This is exactly what we wanted. So let's see what's going on here. We look at the function, our PV function at point 0. We check what is the tangent line here. We look what is the 0, what is the root of this tangent function. This is somewhere close to 4. So this is not exactly the same as the root that we are looking for, the 5 something, but the thing is, it gets us closer to that root. So what we can do now is we can repeat this procedure. We can look at now starting point somewhere 4, check what is the tangent line here, and see where this will get us. So let's try to do this. So let's create another tangent line. Let's call it tangent 4, because this will be the tangent at point 4. So here, now we're going to start at 0.04, right? We're going to look at the derivative at 0.04. And also we need to adjust this guy, because we're going to be 4 steps ahead. Yeah. So so that our tangent line is starts from 0. We need to decrease it by 4. You'll see what I mean in a moment. So again, we add this line to the plot. Run it. Yeah. So now, as we were starting from point 4, we check was this tangent line here. We go along it to find the root, and we see that already here we got very, very close to the yield to maturity that interests us. Okay, so we understand what what Newton-Rhapson method does. Now let us use it to calculate the yield to maturity of our bond. So let's define another method. Yield to maturity, self, and this time it will take price as argument because we are calculating yield to maturity based on market price. So let's say that our initial guess is 0, and we're gonna improve this guess. So we're gonna use this relationship here from Newton-Rhapson, and so this will be x minus f of x. So in our case, this will be self PV at point x minus price. Yep, and this is the f of x bit, and we also need to divide it by the derivative. So we're going to use self PV derivative, and here we also are going to use point x. Yeah. And we're going to return x. But this is just one iteration. We want to have several iterations until we get close enough to the real yield to maturity. So for that, we're going to use a while loop. So while the absolute difference between price and what we get from our next guess, so basically what will be the PV, right? So we're going to use self PV at x okay, while this amount and also let us round it so that as we did for the PV, so that we have 2 decimal places precision. So while this rounded amount is bigger than 0, we will repeat this. Okay. Let us now try to see if our method works. So first of all, let's print what is going to be our bond yield to maturity, given that price that we defined here. Secondly, as a sanity check, let us see if this fills the definition of yield to maturity. So if we calculate the PV of the based on this yield to maturity, so let us create a variable for that. So here we're going to print it. Then we're going to calculate the price based on it, and we expect this number to be the same as the original price, right? Because this is where we started. And let us also plot it on the graph. So we're going to use PLT So it's going to be, this is a function that plots a vertical axis line, and x equal to unit maturity. Okay, let's see where this gets us. Looks like we didn't really get there. Actually, okay, so we get 517.5. The price is fine. It's just that here we just need to multiply it by 100 because this is in percentage points. Yeah. So we actually got it right. Yeah. As you can see, our yield to maturity is 517. This is what we expected, and we got there pretty quickly. Yeah. So let's actually check how many iterations did we go through. So for each of those, we're gonna print our guess. Yeah. Let's run it again. For now, we're not gonna use the plots. So we have 1, 2, 3 iterations. Of course, the number of iterations depends on what is our initial guess. With 0, it's a good guess given current market environment. But let's say that we were starting from somewhere else. Let's say that which is way further. So let's say we start with 20%. So in that case, we have 1, 2, 3, 4, 5, 6 iterations. Yeah. So of course, the number of iterations depends on the initial guess. Secondly, it depends on the precision that we want. So if, let's say, we didn't want to have 2 decimal points precision, instead 0, and we run it again, then we have 1, 2, 3, 4, 5. Okay, so one less iteration. But of course, we lose the precision here, right? So the price is not exactly 91. Okay, so we see what is the sensitivity here. Now let us talk a little bit about the limitations of this Newton-Rhapson method. So first of all, is it working always? Is this method working for all the functions? And the answer is no. So basically there are several things that can disrupt it. First of all, if a function changes the derivative a lot, the sign of the derivative, then just going up after the derivative will end you up flying around. You will not point nicely to one root that you're looking for. If, imagine for example, function like sine, you can even end up in a infinite loop because you'll be pointing back and forth to the same points. Okay, and well, functions can have multiple roots, not just one, and obviously Newton-Rhapson only gives us one root of this function, and it is also not necessarily the closest one. But having said all that, the more a function resembles a linear function, which in our case, which is our case, right? Because if we look at the graph again, as we discussed in the beginning, the function that we're looking at is not very far from linear. Yeah, so it works pretty well in our case. We made some assumptions to simplify it. So we assumed annual coupon, and basically we didn't look at any broken period, right? So we had the full years here. So the thing is that the PV of this bond function can get more complicated, and the question is, what can we do then? Are we going to calculate the derivative of a more complicated function? Well, there's actually another solution, and that is what we could do instead. We could simply calculate a numerical derivative. Okay, let's do just that to see if this works as well. What do I mean by numerical derivative? So if we have a function that we don't know how to calculate the derivative of, here it was not that difficult, but it could be much more difficult, right? But we still want to know more or less what the derivative is. What we could use is simply this definition of a derivative. Okay, let's try to do this as well. This, let's call it a numerical derivative, and here we're going to return this exact ratio here. So we're gonna use the self PV. This will be the nominator of the function, right? And this will also be based on the dependent variable will be, of course, also interest rate. And here we make a small increment, like in the definition of a derivative, like 1/10 of a percentage point. We look at the difference between this point and the original point R, and we divide it by the increment, which in our case is simply this small epsilon that we bump the function by. Let's see if this works as well. Let's run it. Yeah, as you can see, we get to the same result. Yeah, we have also 517.5. So if you are too lazy to calculate the analytical derivative yourself, or you forgot all the high school mathematics, all you need to remember is the definition of a derivative in order to use this method. So I hope you believe now that this is a quite powerful method. I hope you find it useful not just in fixed income but also in other applications. You can find the mathematics used in this episode and the code at infermath.com together with other courses from mine. That's it for today. Thanks for watching, and I will see you next time.